Hey yo, welcome from the stream. As usual, a new day, new video. This is Godro, and as usual, today we're gonna solve some legal problems. So the theme is about mage and forest adventure. We're gonna try to solve binary tree problem. So now we have six problem. We'll try today to solve two or three of them. So we have the maximum depth of binary tree and the deepest part of or a leaf similar tree with the depth of binary tree where the title is the towering canopy. We're gonna try to explore the deepest part of a mystical forest to uncover hidden secret. And the second problem is gonna talk about comparing enchanted tree to decode message hidden in their leaves. For anyone who played League of Legends or know League of Legends, so there is the Champion Rise, who is the one of the mage character. So without further ado, don't forget to follow me on GitHub. Don't forget to follow me on LinkedIn or on Instagram. And recently we did a Discord server. You're all free to join it. And without further ado, let's go to the lead code problems. So the series is the lead code 75. So this is it. We'll warm up with easy problems. Let's just adjust that. Okay, so here. Okay. So given the root of a binary tree, return at maximum depth. A binary tree maximum depth is the number of nodes along the longest max form the root node down the farthest leaf node. So this is the case. Let's just use a new way of understanding the things. So this is our binary tree. Where's the pen? Where's the pen? Man. Okay. Close here. Just get the lighting. Okay, so we're looking for the pen. It's not here. The pen, guys. Hey, hello. Are you getting interviews? So basically, I'm not really searching for jobs because we already have internships in in this period, and yeah, I'm sending some CVs, and I'm getting some response, but it's not the best companies, you know. So yeah, I'm getting some feedback, but it's not the much, and I'm looking for more. Welcome stream, by the way. Hey, the pen, guys. Where did it go? No, man. No. It's not good. Okay, so just gonna shut down the camera for a moment and So, oh, this is too bright. Let's mount the luminosity. So I think. Okay, so that. No. It's not that. Okay. So I think we're good. Sorry for the technical stuff. So let's begin this problem. So the DFS, there's two way in the binary tree. It's the DFS and the BFS. So the DFS is the depth in first search. So we're gonna go to the depth of the binary tree. Let's make a green color. So we're gonna go this, and if we don't, so this is the leaf. We're gonna go to the leaf, and then we return to the this node, and then go to this node, and we discover those leaf, and then we return. The BFS is by level. So the BFS we're gonna need to see those by level and then this level, but in this problem we're not gonna need this. We need the DFS. So to return the maximum, it's pretty, I think it's not that hard. We'll start by, so in current we are here, this is the current position. We'll simply try by searching the two sites by recursive function. We'll search for the two sites, and for every node we'll search in the two children node. So yeah. So the first test case for the the break, when it's break the recursive, if there is only one node, which is 3, let's suppose there is 3 and there is no children leaf, so this, the max, will return 1. So I think in this case we return 1, and we return 1, and for every node it has children nodes. So to continue, in order to continue, we have to, this node have children node, which is not, so we're not gonna continue in this node, we're gonna return. Okay, so I think this is clear. Let's code a little bit, and then if we have mistakes we'll return back to this explanation. So okay, let's do it. So I have 3. So I think here if root, then we're gonna simply return. Okay, so, and we have, no, we don't have to make it, we have to just return max. So if root, or if root to left and right to left, okay, or think we need or. Then we return we have to make it recursively. So let's check. I want to check the stream. If the stream going well, a chat. Type if the stream is going well or not. Okay, so I think everything is good. If root. Oh no, if not root. I think it's not root, because if we go to the end, so there is no root, we're simply gonna return. Okay, so if not root, return. Else, we're gonna do it recursively, so we're gonna check, or I think we don't even need the checks. Also, so we're gonna return 1 plus. So in this condition, if we have only one root, like we said, if you have only one root, then we're gonna return 1. So the 1 is the basic condition, and then we have every time to check for the left child and the right child. So for max depth, we're gonna make it recursively, and this is self dot root dot left plus, and we're gonna make the max of them. Okay, so and the max depth of the right one. So self dot root dot right, and then we have to return the max. Okay. Why is it not defined? Max depth. Okay. Put a lead code in your let may get more views in your title. Oh, okay, not. Oh, okay, self. Yeah, self. Thank you. Hey, welcome stream, boss. So yeah, if I get lead code, it may be yeah, but I'm not really focused with views, man, because it's not the objective of this channel. It only open it to benefit you and benefit me, and I'm not really have the urge to earn views, but yeah. So okay, self dot self dot max depth, and for that we have to make root dot left. Bro, you can't do that. What do you mean, what? Do something because you're calling the function inside function. Yeah. Okay, so There is no problem with this. So the max is not. So the max is not working. Okay, so support between answers of non-type and non-type. So I have to make them int. It's gonna return int. So don't know why it's not. Okay. Good luck on your journey, brother. Been following you much. Hey, thank you, man. عزيز جوك بيه. مرحبا في الستريم بابا. line 10. line 10. If not root or something can return it. line 10. You need to return something. Oh, okay. I'm just simply going to return root. Oh no, I think not. That's not it. What's it? Oh, we have to return the max. No, we return the max here. So so while no recursive, we don't need while. So if not root, okay, we can do that 0. So let's check it. Hey, thank you, man. So this is good, I think. Hey, we're good. Oh, and the runtime is good actually. Okay, so let's just see other solution. Okay, so the recursive. So we can work it with depth first search and breadth first search, like I said. Okay, so max. There is it. Equal max plus 1. Okay. So what is it? Is there also solutions? Okay, so this is it. It's now 80 minutes. Yeah, not bad. So we were finished with this problem. Now we're gonna do this. So leave similar trees, which is this problem. Hey, hope your day was good. Hope everyone is doing good. Keep grinding, keep coding. And let's go. So consider all the leaves of the binary tree from the left to right order the value of those leaves from a leaf value sequence. Okay, so for example, on the given tree, the leaf value sequence 6, 7, 4, 9, and 8. Two binary trees are considered leaf similar if their leaf value sequence same. So return true if and only the two given trees with head nodes root 1 and root 2 are leaf similar. So okay, so the leaf or the order of the leaf also have to be similar. Okay, so this root 1 and this root 2, and you're gonna return true. This is false because the order is not the same. Okay, let's do it. So I'm gonna make this here and that here. Okay, so we're finished with this. Just put it aside and let's go to this. Okay, so to make things clear, so I'm gonna apply the DFS another time. We're gonna search. Oh, or actually, we can use BFS by order. Okay, let's just think of it. Okay, so this 3 and then this level and then this. No. We're not good. And also this. Oh, so we cannot use the BFS. The BFS is wrong. Okay, so let's just put away. Okay, so I'm gonna mesh. Oh, so when we reach a leaf, I think we can make them in a set. No. The set doesn't have indexes, so it's not ordered. And if we make it in a list, we make them in a list. And then compare the two lists. Okay, so I think this is good. Okay, I think this is good. Let's just test it. Okay, so and if we have only one root, I'm gonna just make it in a list and then okay. So if the root doesn't have any left or right side, then we're gonna add it to the list. Okay, so I'm gonna initialize to list. So I'm gonna make it R1 equal and R2 equal. Okay, so these two lists, I'm gonna iterate through every one of them. Can we iterate them like in a parallel way, like simultaneously actually? Can we do it, or just iterate one node, one binary tree and then the other? Hello, dude. Hey, thank you, man. Hello, welcome stream, man. So let's make the condition if think if not root, let's make it. If not root 1, no. No, we need a condition to stop. If not, are we gonna make them simultaneously? So if not root 1 and not root 2. Okay, so I'm gonna make one for root 1, return 0, and so this is the structure. So if not root 2, I'm gonna return 0. Okay, but then we have to, well, actually we don't have to return, we have to append every time to the list. So every time so if we're gonna append them, if not root 1 dot left and not root 1 dot right, we're gonna append root. So r1 and dot then we have to call it again, or append. Are we gonna make it for or do I have to make another I think I have to make another function. So let's call it not here, what? Okay, so I have the idea, but the syntax and the recursive thing, I'm not able to solve it. So I'm just gonna this. Okay, so if root but now I have two roots, so even in the parameter I have to pass two roots. So if not, how am I gonna do it? So the first and leaf. what is that? So okay, yeah, so I have to add it. If not root, and if not root, return. Okay. Okay, so print root data. So if not root, and but I have two nodes, so to root. Yeah, so this is what we need. So if not root left and not root one dot right, we're gonna append root. But that have to be recursive, so I think I'm gonna oh. So where it's, so check if leaf recursively. Just okay. Or can we append it simultaneously in two different, like from r1 dot append. Okay, so I think I have to print this, and if root to the left and root to the right, r2 append. This is root 1 and this is root 2. If not root 1, return. So when he's gonna continue. Okay, so those are the condition to stop. I think I have to make this end. So if not root, return append dot data. I'm not gonna append the node itself, but it's data. So dot val. So dot val, and every time it's gonna compare. And after all that, or no, append. If not root 1, append. I have to make the recursive here. How I'm gonna make it? Okay, chat. Hands. Now it feels trivial. Okay. Hey yo, how many chat do we have now? Okay, so yeah, it's 5. Okay. So I have 5 simultaneous spectators. Welcome everyone. So I think here we have to define a function, because it's not logic that every time we recursive this, so it will initialize another empty. So I'm gonna make a DFS, and the DFS will have the Okay, so we'll have the root, I think. Okay, we'll have it root and it leaves. It leaves as parameter. Interface. So when we're gonna stop? Fair chat. It's very long. So when we're gonna stop? So every root will have it leaf added. If leaf doesn't have a right or a left. So if we have only one node, if not root, I'm gonna make if not root. So now I'm just gonna return else. Else what you're gonna do? We're gonna append the leaf. If man, I'm stuck. I'm really stuck, man. So let's get rid of all of that. Okay, so if we're gonna add if the leaf doesn't have leaf. So if leaf of the root. For every root will no. Hey yo chat, it's too long. I'm gonna look for the and see if it's the so if node return, so it's not gonna do it recursively. I want a recursive thing, so fs for line Python solution. So find leaf self and root. Root and leaf. I was wrong. So self and root. If not root, then I'm gonna return this, and yeah, if not root dot left or root dot right, we return the number itself, root dot val. And then after all that, we're gonna return to each one self.dfs root left plus self.dfs root right. Okay, and then we just have to compare the two ones, so we don't need that anymore, so just return the self.dfs root1 equal self.dfs of root2. Yeah, the approach is good, but I think I didn't know how to continue, man. So that's not true. Oh yeah, have to make this a def. Okay. Okay, so let's go. Fuck, man. Okay, so we're good. So we're good. Oh man, I always had the idea, but the the code itself, sometimes I don't know how to write the code itself. So I have to master the recursive thing. I'm not really good on that. So so I have the condition to break and a condition to and then we return every time, and then we call it back. Okay, so fair enough. It's for 2 minutes, I think. I think I don't have. If I make it, okay. So let's just do it. Let's do it, and but I have a. Okay, so given a binary tree root, a node x in the tree is named good if in the path from to root x there are no nodes with value greater than x. So return the number of good nodes in the binary tree. So I didn't. Okay, so given binary tree node x and the tree is named good if the path from root to x there are no nodes with so from 3 to 3 there are no greater value than 3. And from 3 to 4, so node is blue, root node is always good node. Okay, so node 4, 3, 4, the maximum value in the path starting from. Okay, so okay, I get it. Okay. So let's copy that. This also, I have finished it. This, and now we'll focus on this. Okay, so a node call it good if the path from the root to the node itself, this node has the greatest value, which means if we're going from 3 to 3, then the nodes are 3, 1 and 3. This node is 3, has the maximum value, so it is good node. From 3 to 4, it's 3, 4, 4 have the maximum. From 3 to 5, 5 has the maximum, so it is good. So okay, that seems easy, man. we're gonna iterate through each one, and uh, we have to store every path to a set or to a list. And then we compare the max, or every time we're gonna append the value of the node and see if it's the max or not. Okay, so what is the logic? Every time we're gonna go to a node, we're gonna add it to the list. We're gonna add the root, and then we add 1. So check if 1 is the maximum or not. If it's not, we're not gonna, so we're gonna count. So we'll make a variable count, and we're gonna do count. We're not gonna increment count. Then we go to 3. So if 3 here is the max, then we're gonna increase count. Okay, and then we go to the other. And we stop when there is no root left and no root right. So, but for every root, we'll have to make another list. So if it's 4, so clean scribble, nice, bruh, write in your editor, lol, pseudo-coded. Yeah, I'm gonna do it, but just I'm brainstorming with think. Then I'm gonna do it. Hey, welcome stream, by the way. So for every path, we need to initialize a new list. Okay. And store with it the. Okay. So it's not very far from this. So I'm gonna define a new function to make the recursive with it. So def, I'm gonna make it dfs self and the root, and for that and then here we're just gonna return the count. Okay, so gonna initialize count equal 0, and then we have to return the count. So but I have to initialize the count also. So count. So the condition for stopping is if not root. So just gonna return 0. Okay. If I only have one node. So I'm gonna return 1. I'm gonna append. So 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 I have to append in every time the root. So I think I'm gonna have the append root dot value. If root dot value equal max of the path, so we'll increase count by 1. No, we have to return count here. So self.dfs of root. I'm gonna initialize this here. Root left and self.dfs dot root right. And return count. Root right. And then I'm gonna return the fs of root. itself. Okay, so 1. Don't know what is going on, so count +1. So count path, if not path of found. I want to see the path every time, so three. So why it is stopping here? Oh, so he returning count. Um, so the root is gonna go to the root, and every time. So I think we don't have to make it here. But how can is that? So can we do them here? No. Okay, so make that here, and but this all of that, and then we return count, and then we return count, and now we return self dot self dot. So this is it. Okay, so 3 1 3 4 1 5. Okay, so we're doing good. So we just have to make this in one path. So one path. When does the path end? So when do we have to initialize a new path? If the root, so I have to initialize a new path for every time the leaf change. So 3 for 3 when 4 changes. So okay, so so okay, I'm gonna initialize it. There is only one mistake. So if you try to initialize it here, and can we make it all in your head? Nice. Hey, thank you, man. It's not really in my head, but so where's the okay. There is only one thing that I don't know where to change the list. So this 3 3 3, and then we have 3 4 5, and then we have 3 4 1. Yeah, yeah. But man, Okay, so there is only one thing that's missed. The path. I don't know how when the to initialize. So there is only one thing. I don't read only the to wrote pseudocode. So I just wrote the clean code. So I'm just gonna step one, step two. Yeah. The okay. For you, especially. I'm gonna write a special a pseudocode. So like there is here. I'm gonna initialize lies noise a counter 0, and we're gonna counter 0. Then we have to yeah, of course, for myself, but I do anything. So in the editor. No, I don't need, man. Yeah, okay. So that's only one thing that is missing. Comments. Yeah. I understand you, man. So let's take on. And then I have to iterate through all the nodes. No, that's how I was supposed to about this. Hey, thank you, man. So on the node, I have to change the path. So change the path list every time what? Every time we are we gonna create a new list every time we so I'm gonna return it, and then if the root equal max the path list, so we're gonna increase count plus, okay, and then I'm gonna return count. So this is here. So self DFS left. So if not root, how I'm gonna append it? So can I append 313 and then no. I have to make so if we have those, if we have this binary tree, so there's one list, two lists, and so there will be three lists. Where is the thing that repeat 3 times? So there is 1 2 1 2 1 2. Okay, no, it's like 1 and then 1 1. So if I find this, if we find this, so if not root, if not root, or if not root dot left. So if it doesn't have a node, we're gonna initialize another one to go to the other one. But no, in this case we don't have to initialize another one. We have to complete this. So we're gonna do it. So keep a queue for visiting on nodes and pass the queue as the argument for every good node increase count. Oh, so we're gonna work with queue. So for every visited one, we're gonna increase queue for the node and pass the queue as the argument, and for every good node increase count. So I'm gonna make it here. Hey, welcome stream, by the way. So I really didn't understand. Yeah, I understand the idea, but the execution I didn't understand. You don't have to explain it, man. It's just welcome stream. So I'm gonna initialize the queue. So queue equal interest, and we pass it here. So okay. So self.root queue, and then I have to pass it here. No, I have to start from the beginning then. Okay, so I think I'm really close to the solution. So I'm I think I'm gonna use chat for a thing. Okay, so we're making an exception to not make the video longer. So can we use cloud? I think it's better. I don't want any other solution. I want my approach to not start from the beginning. So use my approach with some logic. So I have a correct logic. So return node, return self, root.val. Okay, yeah, maybe that's a different approach. Yeah. So as we said, if not root, I'm gonna make DFS. If not count, gonna return 0. Count equal 1. If root val. Oh, it's max. So he's gonna initialize a max counter. So every time he's gonna add 1. So max equal root. So and then he's gonna add that to the count he's gonna iterate the left and the right. So count if this is, if the value will now, oh, so there is no list, there is no list, but the max so far will be here. So max so far routed far. Okay, so no, I don't need, so if not, I don't think I need even a path. So if I'm gonna make a max so far equals 0. Okay, so if root, and don't need this, and also I don't think we need that. Okay, so if root.val is greater than max so far, so we're gonna append a greater or equal. I'm gonna append count. I think this can work. So Q, no. Okay, so Q. Okay, so return count. He's not gonna return count here, so I want him to return count there. So do I have to pass in the parameter? So count equals 0, no, count will be count. So count and this will be count, and that will be count. And then what? So I'm gonna correct it, but I want to use my approach. Wanted to use it. Use my approach, my syntax. Max so far. So I was gonna make in the parameter max so far, not the count. So if not root, then he's gonna return count, and then he's gonna increment every time count. He's gonna compare, and then yeah, that's okay. So I think with that we're gonna end our stream. Thank you everyone for watching. This day we did a 2 good lead problem ourselves, but the third it's a little bit too hard. It's not too hard, but I'm not really used to it. Maybe in the next videos I'm gonna work on it better. Thank you everyone for following. Thank you everyone for commenting. I really appreciate all the support, all the help. Thank you everyone, and hey, welcome to stream, man. So here we'll end our stream. Okay. Question I have. Okay, you can ask it. We are already ending our stream, so let's copy that and make it here. So the runtime is at its max. Let's see other solutions. Okay, so in Java, first time, what? Hey, welcome stream, man. Oh, 2 lines in Python. Okay. Hello, keep up the good. Hey, thank you, man. Project do you comment? Kind of portfolio. That depends on what field do you want to work on. It's like the project of web development is not the same as mobile, as I don't know, cyber or data. If you want to specialize in AI, there is project. If you want to specialize in development, yeah, like you said, what the field do you want to work on? If you want to work on development and React type, uh, so you can build the basic one, like the to do apps and things like that, to just, yeah, you can start from e-commerce or like a project. Well, 3D, you have to use 3JS, so I don't know if that. Oh, you mean the e-commerce have to be 3D? Yeah, yeah, it is a original idea, but you can work on React when you fetch data and you have product and you have all that. Try to implement the method. Try to understand the method of use state, use effect, handle input, handle submit. Try to understand all that by working on those projects. And yeah, so one line in. Okay, so minus one distance. What is that, man? Okay, let's understand. So return self good node, max. Oh, so he's gonna compare this with the erval, and then self erval plus erval if r else 0. Go army home. Go cyber. Yeah, so it's gonna return every time. It's gonna return it with minus 10,000. 10,000. It's gonna return the erval and then plus erval. I really don't understand that. If r, so if it's root. Erval is gonna be it's gonna be it's gonna be always superior or greater than MA. So it's gonna just, so 3 plus 1 plus 3. Well, in my country, Tunisia, people don't work often in the public sector. The public sector is saturated as hell, so everyone is working in private sector. Well, there is a lot of privilege in the public sector, but man, it is really saturated, and the government doesn't hire people anymore. So I really don't understand that. So I want him to explain it. So it uses default maximum value. The method recursively traverses the tree for each node, does 3 things in one line. So recursively process the left side. Add 1 if the current node is good node. Our value if max seen so far. Okay. Okay, so I did MA max seen so far and value if Okay, this is good. So with that, I think we're gonna end our stream. Thank you everyone for watching. Thank you for the support, for following. I really appreciate your help. And as always, see you tomorrow.